So we can move on to our second presentation, which is Aaron Coombs, who is mentored by Dr. Hernandez Ayala, who I see is here. Would you like to introduce Aaron?
Definitely a pleasure. So thank you, Ariana, and thank you, Lynn, and everyone else that is here for hosting and giving us the opportunity to see all the wonderful presentations. It is my pleasure to present Aaron Combs research that we were able to do this summer. I'm very excited to see what Aaron's going to be presenting. We've been working really hard on this fascinating topic on how clouds, right, the relationship between cloud cover and climate change. So without further ado, let's take a look at what Aaron has to say about that.
Thank you so much, Javi. Really appreciate your nice words of introduction. If Ariane, if you wouldn't mind, I could share my screen and show the slides. I also put the slides in the box link for your future access. But here, let me do that right now. Share screen. Okay. Is my screen viewable to everybody? Perfect. First of all, good afternoon, all. I just want to start off by acknowledging my voice is kind of dead. I was at a concert last night, so hopefully we can make it through, but I think we'll be fine. Today, my name is Aaron Combs, and today I'll be speaking about my project in trends in global and regional cloud cover, and it's their relation to climate variability and climate change. So for a quick introduction, it's important to first understand that climate change is driven by a variety of cyclical factors, including cloud cover. And clouds are a really critical missing puzzle piece in current climate modeling, as you'll soon learn through my literature reviews. But that's mainly because they're both physically complex to model and they have a significant impact on warming. They can drive both warming through absorption of shortwave or thermal radiation, but they can also drive cooling through the reflection of long-wave radiation, which is also light. And it goes without saying that clouds are integral in a variety of meteorological processes, therefore necessitating this research. And for my project, we kind of sought to answer two key questions. Firstly, we wanted to know, how has total cloud cover changed over the past 8 decades? We looked at this question from both an annual basis and a seasonal basis. Secondly, we sought to examine how total cloud cover correlated with other climatic variables. We looked at this question also from an annual and seasonal basis, and for both questions, analysis was conducted at geographically specific locations, the reason for which was to be explained. To establish a scientific foundation upon which I could conduct my research, I conducted a broad literature review. Here, I noted some key papers that helped me narrow my focus and direct my methods. For example, in Croak et al., the authors identified global mean temperature anomalies and pressure systems as key variables to include in cloud cover analysis. Later on, in Durio et al., it is recommended to examine cloud cover over seasonal and diurnal timescales. This is later confirmed in Zhou et al., where the authors identified that decadal cloud feedback deviates from long-term trends. Eastman et al. Drove home the point that it was critical to look back at changes in localized regions, rather than at a global or intercontinental level. Hofer et al., Mao et al., Pletnikova, and Saul would all then set the standard for this specific geographical analysis. As you can see here, we have Zhou et al., Hofer et al. Finally, regarding data itself, Norris, 2000, explained that there are 2 separate data sources from which the vast majority of cloud cover data is derived from: land-based synoptic weather observations and space-based weather satellites, each of which have their own set of benefits and drawbacks. Wu et al. Then concludes this, demonstrated that the ERA5, a reanalysis dataset that includes land from both sources, is the most accurate. Next, we're going to take a quick look into the data I used for this research project. For my project, we sourced our data from the ERA5, a global reanalysis dataset. Just to quickly explain what that means, a reanalysis dataset is a comprehensive and consistent set of climate and weather data that combines observations from various sources, such as satellite data, weather stations, and also ocean buoys, with a numerical weather model to create a continuous and consistent record of past weather conditions. The ERA5 is widely used in climate research. and as stated previously, is currently the most accurate dataset. For our research, we focused on 5 of the many variables included in the dataset: total cloud cover, 2-meter temperature, total precipitation, sea surface temperature, and mean sea level pressure, of which you can see the abbreviations are included here. I also included a screenshot here of an exported cleaned up version of the ERA5 dataset. I don't exactly remember which geographic location this specific dataset was for, but you can see that, for each of the variables, TCC, 2MT, SSC, MSP, and TP, we have an annual column that shows the data averaged over an annual scale. And we also have seasonal values. DJF, of course, correspond to December, January, February, March, April, May, June, July, August, and September, October, November. For our methods, we broke up our overall process into 3 clear stages. Stage 1 was focused entirely on total cloud cover plotted over time. Stage 2 examined correlation through linear regression between total cloud cover and each of the 4 other variables. In stage 3, built upon stage 2 through multiple linear regressions. We also conducted stepwise analysis at stage 3 to determine the most significant variables in our MLR graphs. And here are our results. From our results, I broke them down by the 3 aforementioned separate stages. Here, you can see time series generated in stage 1. These are selected because they represent the wide range of results in this stage that arose. It's clear from this data that while the Earth may be rapidly warming on average at a global scale, this increase in mean temperature does not have a homogeneous effect on all areas. You can see, for example, in Greenland, there's a very clear increasing and decreasing pattern in total cloud cover, whereas in the Sahara Desert, there's a clear decreasing and increasing pattern. So it's really important that as we establish in our literature review to look at our information on a geographically specific basis. Here are just some more charts that we generated. I also wanted to kind of draw your attention to the Indian Ocean and the India graphs, showing that there's clear parallelism based on an ocean that an area is located next to or adjacent to, and the changes in cloud cover over that specific land mass. And I think that that's particularly interesting because it does drive home the previous understanding that we've had regarding the importance of sea surface temperature on total cloud cover. In stage 2, total cloud cover was then plotted against various other variables on an annual and seasonal basis, and linear regression lines were generated. For stage 2 onwards, I selected geographically specific locations based on the severity of the impacts of climate change. For example, we included the Sahel here because of imminent famine. It's located in an area that's largely driven by climate-related phenomena. And what you can see in these graphs is that not only do we have our linear regression lines generated, but we also have R-squared values plotted. For those unfamiliar, R-squared values indicate the percentage of variability that is explained by the linear regression line. A higher R-squared value indicates a stronger correlation between 2 variables. And for these plots, the R-squared values that are important to note down are those that are greater than 0.3. This is because in the final stage, here's just some more graphs. Location and time combinations that any graph with an R-squared value above 0.3 were then selected to undergo further analysis through multiple linear regression and stepwise analysis. I conducted this analysis through RStudios, and I've included a screenshot of both results and the code used. Above here, these results show the variables that contribute the most to the overall multiple linear regression R-squared value and how much they contribute. For example, here you can see that I was working with the Central America winter time data set, and you can see that total precipitation contributes the most significantly to the multiple linear regression. And then in second place, you have MSP, means sea level pressure. You have in third place, you have sea surface temperature, and in fourth place, you have 2-meter temperature. And in the code, we are kind of here just to quickly explain it. We're calling back to the data set that we imported into RStudios. And then later on, we then use it to kind of, there's a quick short piece that helps us generate our answers here. And so the selection summary here shows contribution. And I also wanted to draw your attention to the p-value. It's kind of hard to see here, but if you see estimated as standard deviation, and then this is error and t-value, and then you see PR and some weird parenthesis value, that's the p-value. And the p-value shows the probability of such a correlation occurring if there was no actual correlation. Our goal here is really to generate data that has p-value of less than 0.05, which is generally the statistical standard. And here, on to our conclusion. Ultimately, we identified a few key themes in our data. First of all, total precipitation was overwhelmingly dominating in our results. It was consistently the largest contributor in every single geographic location and temporal timescale we conducted multiple linear regression on, had total precipitation as a significant factor. And while this on the surface is pretty obvious, right? It makes sense that if there's more rain, there's probably more clouds. It does drive home the point that scientists must be studying clouds in order to better understand and predict drought in various locations. This is particularly interesting in areas such as East Africa, which have been undergoing long-term droughts and could have had limited research conducted on their cloud cover. Secondly, and this time surprising result, is that sea surface temperature was the second most common indicator, appearing in 21 out of 46 entries. And when it did appear, it was often a stronger indicator than 2-meter temperature, suggesting that oceanographical dynamics are a critical factor in the analysis of clouds and precipitation. And finally, while mean sea level pressure was the least common indicator, it was often the strongest indicator when it did appear, even if the area was generally landlocked, such as Central Africa. I've also included some notable and unexpected results. Like I mentioned above, Central America has notable results based on its landlocked nature. Furthermore, in multiple areas, such as Central America and Eastern Europe, the dominating factor, not including total precipitation, changed based on the season. In Central America, winter and summer were driven by mean surface sea level pressure, whereas for the spring, sea surface temperature was a dominating factor that was driving total cloud cover. And this really harkens back to the importance of temporally based research, looking at, even within a specific location, looking at a seasonal based data. And it also really it leads us to some questions that researchers can use later on in further research to seek to understand the various physical processes that might be resulting in the different weightings of these variables. I also wanted to note that in one example in the Western US, which is an extremely geographically and topographically diverse area, for our data, the ERA data set, the US West stretches from the Pacific Ocean, California, Oregon, Washington, all the way out to Utah and Colorado and New Mexico, which means you would expect there to be not necessarily a significant impact of the ocean, right? Especially if you're far away in the Rocky Mountains. But not only did all 4 variables consistently contribute to TCC significantly in the winter, but regardless of mountain ranges, the West Coast area was primarily driven by SST as the second largest variable, which I thought was very notable and interesting to note down. And I've also included some references here of the papers we used during to help guide us and really inform us methods. Thank you so much for listening. I also want to take this time to thank Javi for all of his mentorship and guidance throughout this entire process. Really could not have done it without you, and really thankful for our possibility of continuing to work on similar projects in the future. Thank you.
Thanks, Aaron. That was an awesome presentation. Let's give Aaron a round of applause. Some Zoom confetti. Does anyone have any questions for him?
What programming language?
I guess I'll ask a question. So what's your feeling about climate change now as a result of all of this work? I know that's a passion of yours.
Yeah. I am very passionate about climate advocacy, and I think what was particularly important for me that I took away from this entire process is that it's more important than ever for policy to be very nuanced and localized. There's no one policy that can work for any large area, and especially in the United States, right? When it comes to climate adaptation mitigation practices. So it's really important that our state and local level governments are involved in the adaptation mitigation of climate change. And I think it just also drives home the need for further research. During our literature review, we couldn't identify any papers that had talked about the impact of various factors on both localized and temporally specific time scales. So I think it just drives home the point that further research must be done, not only to drive our understanding of how climate change is impacting various areas locally, but also to help inform policy decisions that may ultimately help us better adapt to mitigate climate change.
Very well said.
Thank you. I do see a question in the chat from Jerry. What programming language? I was working in RStudio, so the language I was using was R.
Did you know R before?
I did not. I had to learn it in 3 days, but Javi was a huge was very helpful in that process, and we had like a 2-hour meeting to help me really get the really work on my ability with the language. And then honestly, it was a pretty straightforward process. Once we created the master code for our analysis, then it was really just copy pasting the names into each of the names of the data sets into the code. There was just a lot of find and replace at that point. So once I crossed like that kind of learning threshold, it became a lot easier. And did I like programming? I think it was great. I'm not I haven't done much programming in my life prior to this, and I thought it was pretty easy to learn and very useful when it came to statistical analysis, for sure.
Yeah, I've been hearing a real lot about R lately, that's for sure. So I think you're ahead of the curve now. It looks like Owen has a question.
Yeah, so how do you feel about like recent talk about how cloud seeding and like, because for example, like I know that I heard that the Mexican government is trying to create artificial clouds in order to alleviate some of its mega drought issues. Like, do you think that that's a good idea or a bad idea? What are your thoughts on that?
Yeah, of course. I think my first primary thought with cloud seeding is the kind of impact of this kind of research on cloud seeding. Because we've been creating statistical models of the impacts of various variables on cloud cover, there's definitely opportunity in prediction and predictive modeling regarding cloud cover and specifically precipitative cloud cover. So I think first of all, research like this can be done to make cloud seeding operations more efficient, seeding at the right times at the right places. I think ultimately, as we enter this process into this period of rapid climate change, processes such as cloud seeding will become kind of inevitable. Like we'll have to depend on them if we want to keep some areas habitable and productive. I ultimately think that it is more of an adaptive and a mitigative measure that can help us mitigate the effects of climate change on specific areas. But I do think that ultimately our emphasis should be on decarbonizing and doing whatever we can to return our atmospheric carbon dioxide levels back to the pre-industrial states.
All right. Good question, Owen. Thanks, Aaron. Your voice held up through the whole thing.
I know, I'm really surprised.
All right.